Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends. Now in this lecture on environmental loads as a sequel, we will talk about current loads, ice loads, dead load, live load, etc. Welcome to lecture 28 of the SwayamPrabha course Maritime Structures offered by Department of Maritime Engineering at IIT Gandhinagar. Friends, when we talk about current loads, the presence of current in waves cause three distinct effects. Let's see what are they. 1. The current velocity, which is in the range of about 1 to 2 meter per second, should be added vectorially, of course, because it is a direction based quantity, vectorially to the horizontal water particle velocity, not to the vertical. Okay, I write it here, to the horizontal water particle velocity vectorially. To compute the drag force, we know the horizontal water particle velocity is influencing the drag force computation. So, we have to add the current velocity vectorially to this quantity. The second effect is it steepens the wave profile. It also changes the wave celerity. The third effect is current enables the structure or the member to generate waves. I should say additional waves. Waves are generated by wind driven phenomena, that we know. In addition to the presence of current on structure interface enables the member itself to generate waves, and this causes additional diffraction forces. Okay, this is additional. But one good thing is these values with respect to the drag and diffraction created by the waves are negligible. So, one can even ignore them. Therefore, friends, the presence of current enhances the drag force, and we should remember drag force is a function of velocity square, is it not? You can just look at the equation. If you remember, the drag force was given by half rho CD dia u dot minus x dot absolute of u dot minus x dot. Remember that? It is u dot. Let me write it clearly because there is a confusion here. U dot minus x dot. So, there is a square term available here, right. So, when I say that the water particle velocity will be enhanced because of presence of current vectorially, then the square term will increase the drag, is it not? On structures. But one good news about it is current decreases with increase in water depth. And it is maximum at the mean sea level. Therefore, friends, small presence of current can cause significant drag. So, we have to be careful about it. Then one may ask me a question, how this is handled in analysis? Literature suggests that current can be handled indirectly as follows. Increase the wave height which reflects the presence of current. Now, the question comes, how much will increase? Increase approximately by about 5 to 10% and then neglect adding current further in the calculations. Further, when you increase the wave height, for example, this is the wave profile we have without current. Now, what I do, I increase the wave profile with current, the wave height is enhanced. So, it also changes the period, right. So, the influence of current on the wave period is called the Doppler's effect. It may enhance the period, it may shorten the period also. Okay. So, these two are possible. This is wave height, this is wave height in the absence of current. This is wave height in the presence of current. I say u dot c, right. This is wave height or wave profile in the presence of current. So, it can enhance or it can in fact change the wave period. We call this effect in the literature as Doppler's effect. So, current can be indirectly handled as an additional load, essentially causing more drag on the system as we discussed. Let us move on to the next one, which is the dead load. As the name suggests, dead load is the weight of any member or material in air. It includes the following: superstructure weight, jacket, stiffeners, piping, conductors, corrosion anodes, decking, railing, grouting, and other appurtenances. It excludes certain things. It excludes the following: it excludes the drilling equipment, okay. The drilling equipment means including the derrick, drawworks, mud pumps and mud tanks. It excludes production and treatment equipment, treatment equipments include separators, compressors, piping manifold, storage tanks. It excludes weight of drilling supplies, Drilling supplies include drilling mud, drilling water or fluid, diesel, any casing, etc. It excludes treatment supplies. Treatment supplies consists of fluid separator, storage tanks, etc. It also excludes drilling road, which are arising from combination of derrick load, pipe storage, rotors, table locators, etc. So, dead loads are clearly classified as weight of the member or the platform overall in air, comprising of certain things. Then comes the next part as live loads, otherwise called as imposed loads. They act on the superstructure in addition to the equipment. Okay. They include dynamic amplification effects, live loads are generally computed using a factor which helps to enhance the load for design purposes. Let us look at what are these factors. Typical live load factor as suggested by the code are as follows. If you want to talk about uniform distributed load, if you want to talk about concentrated load, on deck, this is concentrated load, on beams. Let us talk about the region. Let us talk about the walkway, staircase, etc. Uniform load is about 4.79 kilonewton per square meter. Live load concentrated on the deck is about 4.38 kilonewton per square meter, whereas on the beam it is higher, 4.75. If you have a deck area which is larger than 40 square meters, then we use only uniform distributed load at about 3.11 kilonewton per square meter. If you have certain areas which are less used, lighter use, okay, areas of lighter use. In that case, this is 11.9, this is 10.95, and this is 267 kilonewton, specific value. So, live loads are varying depending upon the member area where you are focusing on. Maritime structures are also subjected to impact loads because of drop objects of cranes. During erection, commissioning, decommissioning, there can be impact loads. So, impact loads are handled or some factor multiplied to the live load. Let us talk about this factor. We say load, direction. Let us say we want to compute horizontal and vertical. If we talk about crane loads, enhance this by 20%, enhance vertical load by 100%. So, the factor is 1.2 then. Okay, let me do it that way, that is better. 1.2, this is 2.0, just twice. Drilling hook loads. So, no suggestions. Lift machinery. So, direct vertical load, add about 1.2, that is 20% enhanced. Rotating machinery, 1.5 and 1.5. Boat landing, you have to add about 890 kilonewton additional, here also 890 kilonewton additional. So, impact loads are handled by multiplying certain factor or enhance the live load by some number. So, for the design purposes, uniform distributed load on the deck is taken as 11.975 Newton per square meter in the drilling area. It can be 71.85 Newton per square meter in the derrick area. It can be 47.9 square meter in case of pipe racks, power plant, etc. So, one can see, friends, there is an enhancement of this, and from the dead load what you have compared earlier or what you have seen in other codes for design of other kind of structures, here they are specifically said where you want to apply this kind of loads. We already said the computing of these loads has lot of uncertainties. They are handled by using partial safety factor. Let us say how maritime loads are classified. They are classified into 5 types of loads. Permanent load, identified as P class. Live load, identified as L class. This is P class. Deformation load, this is on fluxural members, called as D class. Environmental forces, called as E class, accident loads called as A class. So, you can divide the forces or loads acting on maritime structures into these groups. Let us quickly see what are these groups. P class loads include time dependent loads. For example, you can say the gravity loads on a gravity based structure GBS can have the permanent load acting on the superstructure because of its colossal weight. The good thing about this class of load is this load can be computed accurately. Therefore, it has lesser characteristic value. The next kind of load is the live load, what I call as L class load. This is associated with operational loads, choice of the characteristic value of this live load depends on the type of structure. Okay. The next one is the D class load. They are loads causing deformation on structures. This load can also be due to temperature deformations, differential settlement, and so on. The next kind of load is called the E class load, which is environmental loads. Arising from the environment. We can give many examples. Let us say wave load, wind load, load from earthquake, load from current, load from ice, and so on. And these loads strongly depend on the return period used to compute these loads. Now, the next question comes immediately in the mind is, what do you understand by return period? Let us say the mean return period is defined as the expected number of years between a given seasonal maximum to occur. For example, you have an offshore deck and you say the live load estimated is about 5 km per square meter. This must be the data taken from the maximum amplitude of live load or any load acting on the deck in the past, let us say 50 years. Okay. The point is, suppose you have taken a record of only 50 years, you get some number. Somebody else takes a record of 100 years, she or he will get another number. So, therefore, we know, looking into the statistics down, this load magnitude may keep on changing, there can be an arbitrary value also arising, right. How to fix this? This is fixed using something called return period. Return period is the expected number of years between which the maximum has occurred. So, for a given load, you fix the return period 100 years, 50 years. So, within that last 100 years, look at the seasonal maximum. It must have occurred 101th year earlier, we neglect that. So, return period fixes the record length up to which you look at the data and collect the seasonal maximum, which is going to be the design load for the maritime structure. Okay. In that case, if the return period is 50 years, let us see, $50, what does it mean? It means that the characteristic load used for the design is expected to occur only once in 50 years. That is the meaning. You assume some seasonal maximum for any value of load, let us say 10 km per square meter. You have taken this load from existing data. That data is, let us say, return period is 100 years or 50 years. Let us say 50 years return period, it means the load what you have taken for the design of 10 km per square meter has occurred only once within 50 years. That is the meaning of that. Okay. Let us try to look at slightly elaborately more about this importance in the design. Now, return periods are used to assess the load effects on maritime structures. Generally, we use something called mean return period. This is actually used to assess the characteristic value of the environmental load. It is the number of years, or let us say expected number of years between a known maximum to occur. So, in the return period, you fix the maximum value first. Let us say wave load amplitude of 6 meters. So, you fix this magnitude of 6 meters and look the data previous from 2026, let us say previous 50 years, 100 years. Look at the data and see when in the data a wave height of 6 meters have occurred, the nearest one or the farthest one. So, that will give me the mean return period of that characteristic value of the environmental load. So, as we said, if the return period is 50 years of any specific load value, then we can say it is expected to reoccur after 50 years, or it is sure that it has occurred only once in 50 years. Okay? What we are interested is not that. We go one step ahead. Let us ask a question, what is the inverse of this return period? Inverse of the return period is the probability that the chosen characteristic value or any load or for any environmental load will be exceeded in any 1 year, that is the inverse of the return period. For example, if the return period is 100 years for a characteristic value of, let us say, wave amplitude, it is sure that it has occurred only once in 100 years. Okay. But we say the probability of the characteristic value which will be exceeded in any 1 year within the 100 years is 1 by 100, that is 0.01. So, the probability is just 1% this value will be exceeded, 99% this value will not be exceeded in the 100 years period. So, now we knew return period and its probability of exceedance in any 1 year, okay, in any 1 year. But we do not stop here, we want to extend this further. That what is our interest? Our interest is what is the probability of exceedance during the lifetime of the structure. I have to connect the life of the structure to this probability of exceedance, is it not? Suppose if 1 by R is the probability of any characteristic load to exceed in any 1 year, then 1 minus 1 by R is the probability of non-exceedance. Can we say that? Okay. So, if the life of the structure is n years, then probability of non-exceedance of the characteristic load in n years will be 1 minus 1 by R of n, am I right? Because probability of exceedance is 1 by R, is it not? Probability of exceedance is 1 by R. Probability of non-exceedance 1 minus 1 by R. So, now if you want to do this for n years, I can raise it to power n. What I wanted is probability of exceedance. This is non-exceedance, right? Non-exceedance. So, probability of exceedance of a characteristic load within the life of the structure will be now given as probability of exceedance 1 minus 1 by R to the power n. Am I right? Because this has become non-exceedance, I am now working exceedance. So 1 minus this. Let us take a quick example and see what happens. Let us say I have a return period of 50 years and the life of the structure is 20 years. So, I should say probability of design load exceeding at least once in the life of the structure will be P20, which is 1 minus 1 by 50 raised to the power 20. Can you work it out how much it is? Let us read it carefully. This is 1 minus 1 by 50 to the power 20. Is it coming to be 33%? Friends, it is very interesting. Any event is occurring only once in 50 years. Let us say in 1980 the event occurred. So, 50 years 2030 the event will reoccur. Okay? But you are constructing platform in 2026, let us say, just 4 years only, and the life of platform is 20 years. Even then, the probability of this design load exceeding at least once in the lifetime is high, 33%. You may wonder, the return period is very long, it will not reoccur within the service level structure, but the probability here is relatively high. Okay, it is quite significant. So, one has to be very careful about this when you choose the return period for this. One can also find out return period based on risk. Let us talk about earthquakes. The design basis earthquake is defined as 10% risk of occurrence in 50 years. Maximum credible earthquake is considered as 2% risk of occurrence in 50 years. Let us see. So, the equation what I am using is R is 1 minus 1 by T of n. Okay. So, now let us see, if the risk is 10%, 1 minus 1 by T of 50, that is the occurrence, you can say that is the period. So, let us find out the return period for this. T is the return period. If you find out how you should do it, you can easily compute this value left hand side, and then you can take 1 by 50th power and then find T. Okay? If you compute T, it comes to be 475 years. So, if you want to find an event which has got 10% risk of occurrence in 50 years, the return period of that event is about 475 years. Long database required. If you look for 2% risk, you will find this T as 2500 years. So, one does not have that kind of record for all environmental load events. So, generally the return period chosen for maritime structures design is about 100 years. The lifetime of maritime structures is usually 20 to 25 years. Okay? So, we use the previous equations to find out what is the probability of exceedance or non-exceedance for the chosen return period. Okay. So, friends, we have studied in this lecture the different kinds of loads, what we call as P load, L load, D load, environmental load and accident loads. They are associated with return period. What is the importance of return period in choosing for the design? We have also seen the magnitude of live load, current, how current influence loads, what are dead loads, what are included, what are excluded, the design and so on. Now we will talk about the important aspect of loads again in terms of ice loads. So, friends, ice loads, earthquake loads, their combination and their effects. In addition to dead load, live load, wave load, wind load, current load, impact load, which are all acting on maritime structures, is a huge subset which have been used and defined in the literature or codes of practice for computing their magnitudes. Okay? So, we will talk about this in the following lecture, and we have now learnt elaborately about the class of loads and type of loads which are applicable to the design of maritime structures. Hope you follow all the sequels in order and try to learn more about them in detail by looking at the reference books addressed to you in the web page of this course. Thank you very much. Good luck.